Uh, Hi everyone, welcome back to the lecture 3 on Introduction to EOB course. Before going into the details of what we will do today, let's take a quick revision of what we did so far. Yes, I suppose. Can everybody hear me? Louder? Is it better now? Okay. So I was saying that before going into what we will do today, let's take a revision of what we did so far. So in lecture 1, we said that Pn is not enough. And we consider some sort of a resummation technique or resummation of this Pn information, which we call as DIS approach, where we constructed the energy function E of x. Bigger. Is this okay? So we constructed this energy function in lecture 1 using the DIS approach. And we said that this energy function is now a better representation of post-Newtonian results. And we did this for circular orbits. Along with the energy function, we also considered a resummation of the flux in some way. And then yesterday, we saw the motivation of constructing the effective one-body Hamiltonian, and we said that the key idea is to combine this Pn information that we have, which you also maybe derived in your lecture 1. Sorry. Pn information with the test body results. Attached to this information, the ring down. Approximately at light ring. And then calibrate this information with numerical relativity waveforms. That's the key idea of constructing a EOB waveform. And then we said when we combine the Pn information with the test body results, we can basically divide the conservative part of the dynamics, separate the conservative part of the dynamics from the radiation reaction effects, meaning that there are now 3 building blocks of EOB. The conservative part, which we discussed yesterday, and constructed the EOB Hamiltonian. Where H hat effective was the effective metric Hamiltonian. This is what we did yesterday. And in the tutorial, we derived the metric potentials entering into the effective Hamiltonian, only focusing on the circular part. But we can generalize it and do it for the non-circular orbits as well. But in the tutorial, we did only for the circular case. The system is not conservative because the the two objects are orbiting around each other and they are radiating away energy in the form of gravitational waves. So there is radiation reaction as well. Which becomes the second block, which we will discuss in this lecture. And then finally, what we want to obtain is the gravitational wave. So we need to also add the gravitational waveform here. So both these things would be the focus of today's lecture, how we incorporate the radiation reaction effects and how we attach the gravitational waveform to the effective one-body thing and obtain the effective one-body Hamiltonian. Yesterday, we also derived the Hamilton's equation so for the test body case. And the Hamilton's equations are so I say that this is the Hamilton's equation are for some Hamiltonian H. I do not specify what this Hamiltonian is. Is it a real Hamiltonian or the effective Hamiltonian? Because we are saying that we want to construct everything, or we want to construct this effective Hamiltonian for E of B. But what we want to actually obtain is the real system analysis. So the waveform that is generated by the two-body system. So it's a real thing. So the Hamilton's equation should also correspond to the real Hamiltonian. And then this H real is related to the effective Hamiltonian using this energy map. And we can insert it back here to obtain this, these equations in terms of the effective Hamiltonian as well. And for the test body case, we saw that the H real is not dependent on phi. So this term is 0. And this is nothing but the angular momentum L dot, the angular momentum loss. So it says that if we are considering a conservative dynamics, the L dot is 0, suggesting that the angular momentum is conserved. But we do not want that. We want to add radiation reaction. So how do we add a radiation reaction to this Hamilton's equation, this equations of motion? We need to add some sort of dissipative force, which we add to this equation as Fr. And here we will add Fy. So now, after adding the dissipative force, the L dot is not 0 anymore, but equal to this force corresponding to phi. And for the radial part, we have this force Fr. And that makes sense because if the body is inspiraling, if the two compact objects are inspiraling, they will radiate away some angular momentum, and that's captured by this forces Fr and Fy. So now, so this is the angular momentum loss. What is the energy loss? Let's look at the energy loss. The energy loss is nothing but E dot is what we want to compute, where dot is a derivative with respect to time. So what is the energy? It's nothing but the Hamiltonian. So what we are looking for is dH over dt, let's say real here, or any h, let's say. Now using chain rule, we can write this equation as basically h is dependent on r, p, r, p, p phi and phi. So we can use the chain rule to write this energy loss in terms of the Hamilton's equation that we just wrote here. So we have dHrr. If we were only focusing on the conserved or on the conservative part of the dynamics, and if we put the equations of motion in this equation, we should be able to get 0 because there are no losses. That's the whole idea of the conservative piece. But that's not the case. We have to add the radiation reaction effects. Now using these equations of motion, into this expression, what we can obtain is E dot is equals to R dot FR. So now this becomes my energy loss expression. And I have angular momentum loss from here, which is L dot equals F of R. Once I have this energy loss in terms of the Fr and Fi and L in terms of Fi, and if I know the energy loss and the angular momentum loss, then I should be able to find what these radiation reaction forces should be, which will lead to this energy and the angular momentum losses. But there is a caveat here. We cannot directly equate the energy loss that we compute in PN formalism with the system losses that we just computed here. And why we can't do it? The reason we can't do this is the energy loss and the angular momentum in PN formalism. The energy losses and the angular momentum losses are computed at infinity, and here we are talking about energy losses and angular momentum losses locally because we are talking about the local dynamics here. Everything is local. And these two would be equal only if we are considering the orbit averaging of the energy and the angular momentum losses. So they both are not equal at every instance. That is, they are not equal at every instance. And the reason why they are not equal at every instant is because these losses are calculated in the near zone of the two orbits, and the energy and the angular momentum losses in PN are computed in the wave zone. So when the losses are traveling from the near zone to the wave zone, they might be self-interacting with the system. So the radiation self-interacts. Or let's say system. And the PN calculation, as I said, is in the far zone. So if they are not equal, so what there comes a term in addition to it to make it equal, where we say that E dot, which is the E dot calculated locally, and these energy and the angular momentum losses are of the system. So E dot of system plus E short. And this short is basically capturing the fact that when you go from near zone to far zone, there are some self-interaction terms. And this self-interaction term is not a non-linear effect. It also occurs in the linear theory as well, for example, electrodynamics. And actually, the short terms were first computed in electrodynamics, not in GR. So if we have this equality, and then we have L dot of the system. And this phi L and phi E are the losses computed in PN formalism. At infinity. Now, if we consider, so basically, how we can compute this E dot and L dot, we insert back the equations that we just computed here, and we obtain what this FR and F5 would be in terms of the energy short and the PN formalism energy and the angular momentum losses, which basically becomes, we have R dot here we have FR and I said that these energy and the angular momentum losses in PN and the local losses would be equal when one considers orbit averaged. And that's it's because the E short and the J short dot terms are total derivative terms. And if I take an orbit average, they would go to 0. So in orbit average, one can say that this is equals to this. And hence, for circular orbits, if we consider orbit averaging, one can say that R dot FR plus phi dot Fi plus phi equals 0, and Fi so one can now find Fr and Fi such that we obtain the phi E and phi J from the Pn formalism. For circular orbits, what is the another condition we have is R dot is approximately equals to 0. And if we fix Fi from this equation, then Fr becomes irrelevant. The radiation reaction force in the radial direction is irrelevant for circular orbits, and we can only focus on Fi. So this equation gives us, for circular orbits, Fi is minus phi j. And from here, we get that this is equals to minus phi e divided by phi dot. And this phi dot is nothing but just the orbital frequency here, which is what? Sorry? Oh, sorry, it's just, it's the same. J is equals to L. If I accidentally write multiple things, just. It's a different way, but it's the angular momentum written in different ways. Okay, now I think we are consistent. So F5 becomes minus phi of the angular momentum, and it's related to the energy loss like this, where phi dot is nothing but omega. So we have Fi equals minus of phi e divided by omega equals minus of phi of L. And we know that this energy flux is nothing but the luminosity that we saw in lecture 1 as well. So this force, Fi, is nothing but the luminosity over the orbital frequency omega. Now, in addition, these are just the radiation reaction forces. But just a quick thing to mention for eccentric orbits, if one wants to consider eccentric orbits. In eccentric orbits, one might not be able to do the orbit averaging, and these E dot short and L dot short term would not go to 0. So how does one do the computation for eccentric orbits? In eccentric orbits, you can consider some ansatz for the short terms, for the energy as well as the angular momentum short terms, by considering some physical insight that these short terms represent the radiation. So they should be, yes? Yes, but in eccentric orbits, the orbit averaging might not be 0. So for eccentric orbits, these E short and L short ansatz you can consider such that these are radiation terms. So they should be proportional to at least the R dot, basically linear in or the odd powers in R dot, the velocity in the R direction, such that you can consider the ansatz and then find what these FR, Fi, and E dot L dot would be. And a reference to for this is Binnie-de-Moore. 2012 computation where they tried to see how these Fi and Fr would change for eccentric orbits. And here we are, for simplicity, considering only circular orbits. Why we need this orbit averaging? We can avoid orbit averaging as well. We just have to compute what these quantities would be. For the circular orbit, this would be 0, and then we compute this E dot short. But since it's a total derivative term, and if I consider an orbit average, this should just disappear. And hence, I should be able to find this simply using FIE instead of going into the short-term analysis. Okay. So basically, we know how to find these fluxes or the forces. Okay. In lecture 1, we already saw that the fluxes in the PN sense are not a good representation, and we have to resum it. So we have to resum these fluxes that would be computed. But in addition to these fluxes, we also need gravitational wave modes. As we said, that we need the gravitational waveform. So the gravitational wave modes we need gravitational wave modes. In GR, gravitational waves have two polarization, the plus and the cross. So basically we have H plus. These are spin-weighted spherical harmonics. In lecture 1, we saw the expression of H up to leading order. But from these gravitational wave modes, we can also calculate the luminosity that enters in the force calculation here. So we said that f phi can be computed directly from the luminosity if we know the luminosity as well. So from GW modes, we compute the luminosity as follows. So this is the relation of between the luminosity and the gravitational wave modes. This suggests that if we have gravitational wave modes, we should be able to obtain the luminosity, and then hence we should be able to obtain the force as well, F phi. But this gravitational wave mode in PN sense in itself is not convergent, just like the fluxes that we saw in lecture 1. So what does this HLM in PN sense look like? Let's see. From H to 2 Newtonian. So the H22 in PN sense looks like this, and this V is nothing but the velocity. If I go to the light ring configuration where x equals 1 over 3, where V square would be 1 over 3 as well, what I find this H22 behaves like is, I will be only talking about the structure of this H22 is like this. We see that every term, as soon as you go to the light ring or even every term in this PN expression is of order 1. So this H22 in PN sense is a bad representation and is not going to converge at all. And hence we need to resum this H22 as well. Now to add the radiation reaction to the system, there are two ways in which we can do the resummation. One is the DIS approach that we discussed in lecture 1, where we were saying that we need to resum these fluxes such that we capture the pole of the flux. So basically,
Bit larger, please.
okay. Is this okay or larger than this? Larger than this? Okay. Okay, so from here, we established that H22 as well as the flux or the luminosity has to be resummed, and PN is not a good representation. So there are two ways. One is the DIS approach that we discussed in lecture 1. So what did we discuss in lecture 1 is, well, lecture 1 was that f of x, the flux, has to be resummed such that we capture the pole in the fluxes. Pole in the fluxes were related to the pole capturing that we did in the energy, because there is no exact solution available for the flux. So we said if we know the pole in the energy, we can, using this pole, find the pole in f of x and obtain the resummed fluxes. But here, this pole, which was basically some function, This pole is the parameter, and we try to tune for this pole such that the waveform that we generate analytically and the waveform that we have from numerical simulation matches. So this is kind of a parameter dependent. Resummation. So this was 1998. This is good, but but we can try to see if we can do something better than what we have here. We saw that H22 in itself is not convergent, and if H22 can be resummed, then we should be able to get the luminosity from the modes itself, and hence the Fy, the force that we wanted to compute. So we try to look for the resummation of the gravitational wave mode, and this was proposed by Damur, Iyer, and Nagar in 2008, I suppose, or 7. In this, we are looking for some parameter-free resummation. And we are looking for the resummation of the gravitational wave modes. And this will become the main focus of today's lecture, that how do we do this resummation. So here, when I write the H22, what I did was I decomposed or factored out the Newtonian piece, though there is no gravitational waves in Newtonian dynamics. What I mean here by factorizing this H22n is the leading order gravitational wave mode. So I'm writing this H22 or HLM as and some factor, which is coming from the higher post-Newtonian orders. I have this factor epsilon here as well. What does this denote? It denotes the parity of the system or the parity of the mode. So there could be two kinds of multiple moments which can generate the fluxes, the mass multiple moments or the current multiple moments. I'm not sure if you studied that in PN course, but it's the same as in electrodynamics as well. And if L plus M is even, we have epsilon equals 0, and if it is odd, we say epsilon equals 1. This is the even parity or the mass moments. And these are the current moments. The difference between these two cases are that the numerical coefficient that will enter in this equation would be different, or in this function would be different. So the basic idea of this parameter-free resummation and resumming gravitational wave modes is to resum this bit of information where the higher order PN corrections are. So we need to resum this piece, and how we do the resummation of this pieces. Instead of doing the additive resummation, we want to decompose this piece as some in terms of some multiplicative factors. So basically, we say that this is a combination of some factors like this. So that's how we want to decompose. And the key word here is that we are looking for a multiplicative decomposition. And why are these pieces? It's not arbitrary, it comes from a physical intuition, and also that this multiplicative decomposition gives a very good result or very good matching with the numerical relativity results. So the two reasons of doing this is some physical intuition of how we can decompose it, and validity with NR. So let's go and and the other thing is all these pieces separately should behave like 1 plus some corrections, because we want to recover the Newtonian piece as it is, and all these order x corrections would be then small corrections. Let's see what these pieces mean and why we have this kind of a decomposition one by one. So let's look at piece 1 with the factor 1. Let's look at this piece first. So what is this S hat effective epsilon? So this S hat effective, the reason why it is S is because it is kind of a source term or a source factor. And the reason why we can factor it like this thing is, consider the test mass case. When we are considering the infalling of test particle in black hole, the kind of equations that we want to solve are Leger-Wheeler-Zedili type equations. And in those equations, the right-hand side contains some source, S, and that source is made up of the T mu nu, linear in T mu nu, stress energy tensor. And for comparable mass case, we constructed the EOB Hamiltonian, and we said that this EOB Hamiltonian should describe the dynamics of the system now. So this T mu nu, the stress energy tensor, should be some combination of this effective Hamiltonian as well as the effective angular momentum. So we can factor this out, and the wave should be are sourced by some sources and should describe the orbital dynamics as well. So this S hat effective is like a source factor. And the reason we choose this is they describe the dynamics, implying that the stress energy tensor should be some combination of H and J. And what this S hat effective would be, it again depends on the parity that we are considering. So for the even parity case, it's nothing but the H effective mu. And here we have J effective. And we consider for this. And here we are normalizing with respect to the Newtonian contribution, the angular momentum effective. And one can also see why we can choose this to be the case for even mode. If we consider the leading order gravitational wave mode, it's nothing but just the energy density. So it suggests that we can write the S hat effective as the energy. Uh, and the leading order is nothing but the monopole, so it's a zero even case. And then for the odd part, it should depend, or the current multipole moments are dependent in some sense to the angular momentum. So we can write it like this. But in the literature, one consider also other choices. But in this lecture, we will consider this choice. And one sees that this approach of factoring out, or this source factor, in some sense captures the DIS pole resummation as well. And why it captures the DIS style of pole resummation? Because we have resummed EOB in such that it should be able to reproduce the test body result when we go to the test body limit. And in the test body result, we have actually captured the pole structure. So this factor of S hat effective is in some sense similar to the pole capturing in DIS. Now the second term, which is TLM. This in some sense represents resumming of the tail contribution. So again, the gravitational waves generated in the near zone travel to the far zone, but the dynamics, or the compact object, also creates a potential. It also creates a potential. So the gravitational waves traveling from the near zone to the far zone would be scattered off by the background, generating some sort of a logarithmic structure in the gravitational wave mode itself. And that's what we want to resum here. And here we only want to resum the leading logarithms entering in the system. And then also this, since it's scattering off this, these waves are being scattered off by the curvature, and the curvature is dependent on the ADM mass of the binary. So these TLMs should, in some sense, also depend on MADM, the ADM mass. Which is equal to the real Hamiltonian of the system. And this TLM is actually a universal factor. If the wave is propagating in any curved spacetime, there would be tail contribution. So it's a universal factor. Whereas this S hat effective is dependent on the source that one is considering. And the resummation of this TLM is where L is the mode that we want to study. And this is a gamma function. And this K, which we have a factor which enters in the resummation of tail contribution, should depend on the ADM mass, because these tails depend on the curvature, or which basically depends on the ADM mass of the system. And then we also have H double hat is H real M times omega. And this K without a hat is nothing but M of omega. And this R0 is the scale in the system. And for the cases we are considering, it's nothing but just 2m. So that's the key thing about the second factor, which is resumming of the tail contribution. One thing to note is we are only resumming the leading order contribution, leading logarithm. Now let's look at the third factor, this exponential I del ln. So this exponential I del ln, or basically del ln, it captures all the remaining subleading terms that we didn't capture here, which could be subleading logarithms or any other effect. So it's like so basically what we are doing here is it captured the source factor. It is capturing some part of the phase, and whatever is remaining in the phase or the complementary dephasing term is now being captured in this del lm, which is coming because of the subleading logarithmics and other effects. Now we have the fourth factor, which is FLM. By the way, how we compute this del lm is just taking a complex ratio between this h to 2 or this HLM and the two factors that we computed from the physical intuition. So del lm is like a complex ratio. What is this fourth factor? It's like a residual term. It takes into account everything that we didn't capture physically. So it's a residual amplitude correction. Yes. Yes, it's exponential I to k bar log of this. So what I was saying was the fourth term. It's everything remaining. Basically the residual amplitude correction. And how we compute this FLM is we take a modulus of the complex ratio between this HLM and all the three terms that we computed. So basically it gives just the amplitude and no phase is there, and every phase effect is included in this del LM. So it's between HLM and one would expect that the pose structure is being captured here. We captured the leading logarithmic terms here. So this FLM should be well behaved in the sense that at each Pn order, the term should be smaller. Unlike the HLM case where we observed that at each Pn order, every term was of order 1, and hence it was not a good convergent series. So we expected that FLM, which could have a structure like this, is such that all these Pn orders are smaller. And the reason for this expectation is the pole structure being captured here, which would usually give non-convergence. And also the tail factors or the odd in velocity factors that were entering in the HLM are now being captured in the tail contribution. So everything which could give non-convergence has been captured. So this FLM should behave nicely. But despite all this thing, FLM for higher modes doesn't behave nicely. Sorry, in the third term? Or it can capture the subleading effects or other things that we haven't taken into account in this TLM, the logs, the tail effects like memory or anything can be there. No, the spin is a different game here. We are talking only about the circular orbit dynamics. The spin you can add as like, for example, here's like a spin contribution term, which will modify your S hat effective in the first place because S hat effective is dependent on this H hat effective. And H hat effective is not of the orbital dynamics, but should also include the spin things. So spin is a completely different thing. I'm not talking about the other physical effects such as spin, tides, etc. Okay. Yes, of the binary. Yeah, but that's okay, even if it's not. But it's basically the mass asymptotically, let's say. Yeah. Okay, so we were talking about these FLMs that they do not behave nicely, despite the fact we expect them to behave nicely. And this happens especially when we are near the plunge or late in the in spiral. So your expectation was behave nicely. And the reasons were air captured already in TLM and light ring like coal captured in S hat effective. But this doesn't behave nicely near in spiral, near late in spiral. And plunge. This function needs more resummation. We need to do something else to this to this function. So what the Murray and Nagar proposed was we write this FLM as the Lth function of some or L to the power of some rho Lm. And the one motivation of doing this could be seen from the H22 mode or the HLM mode. When we consider the HLM mode at the Newtonian order, it scales as omega L RL harmonic. Some v to the power epsilon, where epsilon now depends on denotes the parity of the system. It could be 0 or 1. And we do not solve anything in the gauge-dependent quantity, such as the radii, which is a gauge-dependent quantity. What we want to do is we would like to replace it with a gauge-invariant quantity, such as x. And in one of the tutorials, we saw the conversion of how to go from u to x or x to u, and u is nothing but 1 over r. So r is, in terms of a gauge-invariant quantity, is like this. So this suggests that r to the power L behaves like x minus L. So r to the power L harmonic, simplicity I'll put this way, scales or behaves in gauge invariant fashion like this, which suggests that it is growing linearly in L. And what it shows is, if I consider, let's say for higher mode, let's say I have L equals to 6 mode. For L equals to 6 mode, this FLM is so at L equals to 6 mode, the FLM behaves like this. This is the leading contribution, and this is the next leading order contribution. If my value of x is such that it is equals to 6 times 1 plus 1.26, it shows that the higher order contributions are of the same order as the Newtonian contribution, and this we do not want. And the other thing, we can also see that at near the light ring, this contribution would be even larger than the Newtonian contribution, suggesting that for higher modes, this FLM is not is going to create a problem because it scales as L, or it's linear in L. So we should maybe try to define a function which is 1 over L of the FLM, so 1 over L power of FLM, and hence in here, this FLM is defined like this. So we have obtained the multipolar decomposition of the HLM in terms of the 4 factors. These 2 factors were physically motivated. This contained the subleading logarithmic terms, and this factor contained all the things that were remaining. Basically, it's like an amplitude residual term. So we have this H hat LM, and we said that if we have the H hat LM, we should be able to compute the luminosity. So luminosity L was the time derivative of HLM square. And this L was related to the flux as, for the flux term, or the force as minus F pi omega. So we have this decomposed, basically resummed, as every factor was resummed. So this H at LM that we computed from multipolar decomposition is well behaved. This suggesting that this force is, or the flux is also nice representation and is the resummed version. And then we can put this back into the equation of equations of motion that we had. So we had dr over dt. This is not visible. Is it better now? Yes, 1 plus 0.26. And I'm saying that if the value of x is equals to 6 times 1 divided by 6 times 1 plus 0.26, this term is of the same order as the Newtonian or the leading order term. And similarly, if I want to put x equals 1 over 3, which is the light ring position, I will find that this term is even larger than the Newtonian contribution, suggesting that FLM is not a good representation and is growing linearly in L and is problematic. So we need to find some better representation of this term. And it would be a better representation if I just take the L out of this expression. So saying rho Lm is 1 by L of this FLM that I defined. Okay, so the equations of motion are the following. So basically now we have Fy. In the equations of motion, we also initially had f of r, but we said for circular orbits, f of r is irrelevant and we can ignore it. So this is the system that we will solve by putting Fy from the resummation here. And then we can obtain the orbital evolution of the orbital parameters, the r, pr, phi, and p phi. And then we put it back in here, and we should be able to obtain the gravitational waveform. So it represents the gravitational waveform of the in-spiral and plunge as well. But here, all the construction that we did was for the circular orbits, and plunge is not circular. So we need to take into account some other thing as well. So what do we do is, this HLM that we said initially was so we begin with HLM being HLM Newtonian. And this higher post-Newtonian order contribution, which we just resummed. And we said that this is not enough if we go to the plunge case, because plunge is not spherical. So we need to add some non-quasi-circular information as well, which we add by saying that there is some residual term which captures the non-quasi-circularity of going from in-spiral to the plunge regime. And we consider an ansatz for this because we do not know this term. So we say that this term is like some 1 plus some a parameter, or let's say C1, which is an unknown and is dependent on PR, blah, 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 all these things. And we try to find this non-quasi-circular parameter by fitting this waveform that we obtain with numerical simulation. So this waveform that we have just obtained here gives the full EOB analytic waveform for in-spiral plunge, with this parameter being fitted from numerical simulations. So if we have the H hat effective as well as this HLM decomposition, and we put everything in this equation of motion, we should be able to obtain the in-spiral plunge analytic waveform. Now, we said we also want to do, so we have done these two things. Now attach the radiation reaction and also the gravitational waveform. But in year B, we said that we also need to attach the ring down approximately at the light ring. So whatever we did so far was only for the in-spiral plunge. Let's look at what do we do with the ring down. Yes, that is what we did when we did exponential I del LM and here. Because this H was, so it should capture both the amplitude as well as the phase. Yes, here and here. Okay, so what was I saying? Oh, let's look at the ring down now. How do we do the ring down? We need to capture the ring down as well. But what is ring down? It's basically perturbation of black hole that's formed after the merger. It's an unstable black hole, and it will perturb to form a stable or a symmetric or static, go to a stable, static or symmetric configuration. And we want to see how we can attach this ring down to this HLM. But first, how we do this computation of ring down? So we use black hole perturbation theory. If you remember in lecture 1, I was showing that depending on the part of the waveform that we are interested in, there are various techniques that we can use. For the ring down, it's black hole perturbation theory. And also numerical relativity simulations. From that also we can obtain the ring down. Or Here we will talk about the black hole perturbation theory, but what does it mean? There is the symmetric of a black hole. It's being perturbed. So there is a background where we have small perturbations to it. We will be focusing on the spherical symmetric case, spherically symmetric time independent case. So this background is Schwarzschild. And again, we said that if we are considering test mass falling into a black hole, the equations that we solve are Regge-Wheeler-ZED type equations. So for QNMs or for black hole perturbation theory as well, when we try to find the equation for this, it's also Regge-Wheeler-ZED type, but without any source present on the right side now, because we do not want to see the effect of the source. We want to just observe how the black hole is being ringing down. So the equation is basically this. This is the master equation corresponding to this perturbation. This is the master function. And if we calculate this master function, we should be able to obtain the perturbed metric or the perturbations corresponding to the metric. Now, here I am using R star, which is the tortoise coordinates. And it is related to the radius R as follows. For Schwarzschild, it's like this. Just one point before we go further is here. When we solve these equations, actually we do not consider R, but we consider the R star, the tortoise coordinate. And the reason is, if we consider the tortoise coordinates, then the matching with the test mass case is better. And also the equations of motion have better stability when we go near the horizon. So here as well, we will use tortoise coordinates, and in EOB, it is defined like this. So that was one other point for the EOB equations of motion. So yes, I was saying that this is the tortoise coordinate. If we look at this equation, this reminds us of Schrodinger equation from quantum mechanics, and where it is just an eigenvalue problem. So here as well, it's just an eigenvalue problem, and these omegas would be, or the frequency would be the eigenvalue, and that would become the quasi-normal mode of the black holes. The potential, this VR is Regge-Wheeler potential. So the Regge-Wheeler potential plotted against R star is like this. We see that there is the function, the potential goes to 0 on both the sides, and it peaks around in between at some point. And we know that it should peak around somewhere around light ring, because that's what we said, the ring down is attached somewhere around the light ring. So this peak and this is kind of a scattering problem that we want to solve. So if there is perturbations coming in, some of them would be absorbed, some of them would be reflected, some of them would be transmitted, and those transmission functions or reflection coefficient is what we want to determine here. So that's what we want to do. Yes. Here? That I will make a comment just right now. Yes. So just as you said, there could be two modes again. So there could be a mass multiple moment or the current multiple moment. And for the current or the odd one, we have Regge-Wheeler equations. But for the even one, we have Zedeli equations. And one would expect that we should solve both of them, and the quasi-normal mode would be different. But Chandrasekhar showed that even if the two potential, the Regge-Wheeler potential for the odd case and the Zedeli potential for the even case quite be too different. They can be too different, but they are related by something called as Dolbeck transformation. And hence the transmission and the reflection coefficients either computed from the Regge-Wheeler or from the Zerilli would be the same, implying that the quasi-normal mode would be the same if whether you consider the Regge-Wheeler or whether you consider the Zerilli. So you have so one can solve a simpler case, which is always the odd case. So it's the Regge-Wheeler case. And for rotating black holes, one would have a Tchaikovsky equation, and then one can solve this equation, and using this one obtains the quasi-normal mode of the black hole. So, and here we see that the waves, since the black hole is radiating away energy, the amplitude would go down, and hence there might be multiple quasi-normal modes, but the one that would be surviving or would be dominant in the ring down would be the one where there is least damping, and that becomes the fundamental quasi-normal mode. So, okay. We just said that since black hole is radiate away energy, amplitude goes down, decreases, and the dominant mode in the ring down is the one which is least damped, even if other quasi-normal mode frequencies are present in the system or get excited, but this will become this will be the dominant mode, and it's called the fundamental quasi-normal mode of black hole. And this is a mode of the final black hole. And this is the real part of the frequency that we said. And the imaginary part of this frequency will give us the decay time of this mode. This is obtained by numerically solving the Regge-Wheeler equations. And the dominant mode in GR is the other term, other coefficient. And using some hand wavy argument, we can obtain this value of 0.38 instead of doing the full numerical computation that one would require to do. And how we can do this is, let us consider that there is some perturbation. So the two black holes, when they merge, they perturb the curvature around it, and this curvature would be around the light ring. So basically what we are saying is, this is the final black hole, and around the light ring, which is R equals Pm, there is some blob of curvature perturbations, and this curvature perturbation lingers around the final black hole, and that's what gives us the quasi-normal mode frequency, and that's what we want to try to estimate. This is just a hand wavy argument, and this is the full numerical computation that one does. So for the dominant mode from gravitational waves, we know that So we want to compute the frequency of this blob moving around this light ring, which we, for simplicity, call also as the ring down. From gravitational wave, we know that this is equal or approximately equal to twice the orbital frequency. That is what we saw in the first lecture as well. And this, from the Kepler's law, we know that m omega square whole square is equals to m over r cube. Now inserting it here, we obtain that this is 2 over m this the frequency of this thing would be approximately like this. And at light ring, we know r is equals to 3m. Now inserting the light ring point here, we obtain that this is equals to 2 divided by 3 square root of 3m. And when we do this computation, we obtain that real part of the ring down computed now using this hand wavy argument is at least up to the 2 decimal points. It's the same as the one that we compute from the numerical values. And one can also do a similar computation for the curved black holes and also for the decaying time. And for the decaying time, one has to do the geodesic congruence around the light ring, and that should give the time decay. Now, the standard picture of combining this, the waveform computed from the ring down with the waveform that we had from the in-spiral, for the in-spiral plunge, was attaching only the leading order quasi-normal mode or the dominant quasi-normal mode. But then it was shown that if we just attach the leading order or the dominant quasi-normal mode, the frequency from numerical relativity simulation doesn't match with the one computed from the analytics. So there was a proposition that maybe we should try to include other higher quasi-normal modes into the waveform computed for the ring down part, and maybe that will improve the picture. So basically we say that h of ring down, where tau is now defined as t minus t merge, dimensionless time basically, should be a summation of over all the modes that we have, not just the dominant one, where sigma, the real value of sigma is the frequency of quasi-normal mode, and the imaginary part gives the decay time. For non-spinning cases, this was working quite fine, that if we say that the full waveform is like this, h full waveform is equals to So if we say that the full waveform is some combination of the ring down waveform as well as the in-spiral plunge waveform that we just computed, and for ring down we use this h, which is the addition of all the large number of multiple moments. For the non-spinning cases, this was working quite well, and this theta is the Heaviside function, and this Tm is the merger time. So we want, before the merger, it should be the in-spiral plunge waveform, and after the merger, it should be the ring down waveform. And if there are any other coefficients that are lying in the system, they should be matched with the numerical relativity simulations. For the non-spinning case, this worked quite well, as I said. But for the spinning case, this additive picture was not good enough. And hence, there was a new proposition, which was the multiplicative picture. So this we say is the additive thing. And now for the spinning cases, one does multiplicative approach. Can I take 5 minutes? Okay. So the multiplicative approach is we have to factor this H ring down such that we factor out the H corresponding to the fundamental quasi-normal mode and then other terms. And this is done by factoring it as AH in terms of the amplitude and the phase. And this phase, as I said, should be decomposed like this. So it has phi of H, which is omega 1, corresponding to the fundamental quasi-normal mode. Minus higher function, and this phi 2 is the phase at the merge time or the merger time. And this AH and this phi H should be like a tan hyperbolic function. The reason why we expect it to be a tan hyperbolic like function is tan hyperbolic have this property that it is 0 at x equal to 0, and then it asymptotes to some value if we go to higher in x, for example. And that's the kind of structure that we expected, because for first few orders after the merger time, we expect that there is going to be a transition and the quasi-normal mode will not build up instantly, but it will take some time for it to build up. And hence, we expect that after some time, this should behave like the H coming from the quasi-normal mode plus some corrections. So it's like asymptotic to some value. So we can say that these two things are tan hyperbolic functions. Once we express them as tan hyperbolic functions, we would have some arbitrary parameters lying in the system, which we can fix. Some of them we can fix from numerical relativity simulation. Some of them we can fix using some physical constraints. And that's how we basically build the ring down part of the waveform and then attach it here in this way and then obtain the full waveform from UB. Thank you.